Hello, everyone. In this presentation, we will discuss the analysis and prediction of flight ticket prices. Here are the steps of our presentation. We discuss our research and the dataset, explain the pre-processing steps, introduce principal component analysis and different models incorporating PCA, show our results, and discuss some limitations as well as future work. So our main goal is to develop data-driven methods to predict flight ticket prices. In the process, we plan to answer some questions. For example, how does dimensionality reduction, in particular PCA, improve our predictions? Also, which methods are acceptable in terms of both generalization and interpretability? Meaning, apart from predictive performance, can we see which features are more influential than others? Our dataset comes from Kaggle's comprehensive flight data, scraped from Priceline.com, an online travel agency. Our response variable in the dataset is the ticket price, and we have a decent number of categorical and numerical predictors. Now we explore some of those variables. The distribution of the ticket price was highly right skewed, so although most flights were below around $3,000, some prices were much more expensive, as seen from the outliers. We also compare the departures and destinations. We see that the John F. Kennedy International Airport, JFK, is the most common departure airport location, while Bangkok International Airport, BKK, is the most common destination. When comparing the predictors travel time and total stoppage time against features like the number of stoppages, which only contain one-digit numbers, we can clearly see that there's a huge gap in the scales. This makes the data sensitive to PCA, as well as some machine learning algorithms, such as K&N regression, which provides the motivation to apply scaling prior to modeling. Although most predictors have low correlation, some variables, such as the number of stoppages and travel time, have high positive correlation. And it makes sense intuitively since more stops implies you are traveling longer. So there were some collinearity issues, which provided some motivation behind the implementation of PCA.
In data pre-processing, we follow our step in this order: data cleaning, splitting, scaling, and encoding. For data cleaning, we perform three major imputations to the data. First, we calculate arrival time information using existing data. Second, to address missing data in arrival date, we employ a random forest classifier, imputing values based on all other predictors. Additionally, we conducted the data consistency checks for the dataset, leading to the removal of approximately 120 records as they are recorded incorrectly. Following the cleaning process, we proceeded with data splitting, reserving 80% for the training and validation. We also performed standard scaling on numerical features and one-hot encoding for categorical variables. Our chosen baseline model is multiple linear regression. This advantage of this model is its interpretability, which is achieved by simply examining the coefficients. However, the model downside is its poor generalization. The testing R-squared score is below zero, indicating a disastrous performance. This is expected given that the data comprises more than 200 features after one-hot encoding. That's the rationale behind our decision to apply PCA to reduce the dimensionality of the data. After applying PCA, we found that first 30 principal components explain 90% of variance in the data. We'll use these components for training the advanced models. To interpret the model in terms of its original features, we decide to apply reverse engineering to PCA. This technique is based on understanding the PCA is merely a data transformation process. We'll go through 5 steps, which include obtaining the PCA coefficients, getting the PCA loadings that explain the contribution of each original features to each PC, performing the dot product between them, and then sorting the results. Through this process, we will understand how each original features instead of principal components contributes to the prediction. This is the flowchart of our project pipeline. The advanced model we trained including PCR, K&N, random forest, gradient boosting, and support vector machine.
So we then use K&N for its ability to handle nonlinear patterns, employing PCA to mitigate high dimensionality limitations, though interpretability remains the issue here. We then selected random forest regression for trials due to its ability to handle complex patterns and overfitting control. We then find travel time and 2 stops as significant features here. So similarly, gradient boosting was employed for its bias reduction and variance control, also highlighting 2 stops and travel time as key predictors here. And the new techniques we're exploring here is support vector regression, which adapts SVM for continuous outputs. So SVR maps data into a high dimensional space and finds the best fitting hyperplane. It focuses on minimizing errors while allowing some deviations with a tolerance margin defined by the epsilon. By balancing model complexity and data fitting, SVR efficiently predicts continuous output with high accuracy, handling both linear and nonlinear relationships. So we chose SVR here primarily due to its ability to handle nonlinear patterns and its robustness against overfitting. So after SVR applications, we analyze the feature importance here. So in summary, gradient boosting proved to be the best model with the highest has R square and lowest MSE, likely due to its bias reduction variance control abilities. Interestingly, PCA didn't enhance model performance, possibly due to its information loss as detailed in our notebooks. However, even with the best model, gradient boosting has to test R square of around 75%, indicating potential overfitting and the need for further hyperparameter tuning and model refinement. Notably, models like random forest and gradient boosting require a lot of training times, and our future work will focus on addressing expanding the data sets and more features that are much more relevant, and also experimenting with more complex models and also adding permutation importances.